Thanks for listening in to the Electric Goddess podcast. While we call these podcast intros, basic battery knowledge is recommended. There's plenty of references out there on the internet, and we suggest that you take anything we say or anything you read with a grain of salt and do your own research. For consideration and clarity, sometimes I'll stop Luke or Bryan to kind of keep on the same track on this particular subject. We appreciate the support and the encouragement, so please leave a comment or like this video if you enjoyed it. And Luke and Bryan have related experience in batteries and electric vehicles, so today we're really excited to talk about cell balancing and how it can be implemented into pack design and BMS design to optimize battery performance and long-term performance. Let's get started. Luke and Bryan, can you help describe what cell balancing is?
Sure. Each cell has a capacity and a state of charge, and in a balanced situation, you would hope that they all are sharing a similar state of charge with each other.
And maybe even to start farther back, this is assuming that you have a battery pack where all the cells are identical. If you made a battery pack where cells were twice the capacity of their neighbors, it would look like it's balanced, but then be imbalanced later on. So from step one, you have to actually make sure that your cells are matched and balanced from factory. So if one has 1 amp hour, it's paired with others that have 1 amp hour, so that then your active balancing system has a chance of leveling out the pack.
Yep, if each parallel cell group has identical capacity, or as close to identical capacity as you can get, then each state of charge will represent an equivalent unit of capacity stored between each of the series groups.
And to most make effective use of the battery pack safely, it's at some point all the cells need to stay matched together. And so this is where active cell balancing comes into play. Because the battery pack, if it gets too high voltage or low voltage on a single cell, it will destroy the pack. So in the end, your pack is only as strong as your weakest cell. And in this case, balancing tries to make the other cells or the weak cell keep up with them.
Yep, or drain the overperformers to match the underperformer.
Which you bring up a point that there's 2 different ways that you could balance a cell.
Yep.
That either by charging or discharging. The simple way is discharging, and then it's just as simple as like tying a resistor on and bleeding, like popping a hole in a tank that's overfilled and draining some of the excess out and then stopping it. And then the more advanced ways are trying to charge single cells and strings to balance them.
And whether or not that more advanced way has benefit for your needs is based on the amount of imbalance that you may be expecting. And in healthy cells, the rate of imbalance you should see approaches only the amount of self-discharge that you're seeing, the difference in self-discharge rate that you're seeing between cell groups. So having an active system may not, or the ability to charge the low cell may not be as valuable as it seems in light of what's causing the low cell to be low.
Right. So to expand upon that, if you have a cell that's self-discharged due to a defect, no balancing system is really going to help you at that point.
It doesn't correct your defect or repair any damage done to your cell causing it to be defective. It does mask the effect of being able to have clear visibility that you had a defect, though.
There's a lot of different concepts in cell balancing. You had mentioned having a pack with all the same cells, right? Or having a pack with a bunch of recycled cells, or trying to repurpose things that are out there. And so even now that we understand what cell balancing is, why is it important or needed? And are there use cases where you definitely should not do it?
Well, I guess the start of your question about using different types of cells, as a product, if you're building something for yourself in your garage, that it's only your risk involved with it, that's one thing. But if you're producing a product that you're selling to the public, it's critical that you're only using premium cells and cells that are matched. By matched, I don't mean necessarily that they had to be hand sorted, but I mean that they were all passing through formation, meeting the same criteria of manufacturing acceptance on quality. And go ahead.
To expand upon that point too, there's actually, we were talking about balancing, but there's two types of balance. And not balancing, but actual balance. There's static balance, and that's when the battery is at rest. And that balance shows you a capacity difference, usually, between the cells. And then there's a dynamic balance, where even if your battery pack was fully balanced during a high dynamic load or a high current pulse, if there's any sort of impedance or resistance imbalance of your cells, it'll show up as a voltage imbalance that then disappears when you let off the throttle and the current comes back to normal. And so the matching of the cells is, like Luke was alluding to, it's not just capacity, but it also has to do with its internal impedance. And so this way, while you may have no imbalance while sitting static, and on a cold day you may show a massive imbalance while under load that disappears, and that's just showing the tolerance spread on the cells. So as Erica brought in of second lifing or mixing and matching cells, it gets very complicated if you are taking cells that don't match up via capacity and impedance and try to use them in an overall larger pack design. Not to say it can't be done, it's non-trivial, and it's very risky to play with cells that may become overcharged in the middle of a pack.
Also, you can get recirculating currents in parallel groups if you have different impedances. Like Brian mentioned, under those dynamic conditions where some groups sag further than others, intra-parallel group, if some cells sag further than others, then you end up recirculating power from your low impedance cells to your high impedance cells during rest periods in the pack. All reasons why you really should be starting from all similar cells. Differences in impedance and age of cells and capacity, all of these things make it a very difficult pack to manage safely.
Thank you. I think that puts a nice warning label on kind of the conversation we're having today, which is cell balancing, considering you're getting your cells from the same source and then they're of the same type and of the same lifespan, and impedance, and resistance.
In those situations, there'll still be some differences because no pack has perfect temperature uniformity. Even in the situation where it's been sitting out over the morning or over the night, and now the sun warms it on one side preferentially than the other side, so that you see these temperature gradients which will appear as dynamic imbalance. However, it may be temporary dynamic imbalance that once the system reaches an isothermal state, that
in the
balance disappears.
In the hobby world, balance is usually referred to as the static balance, but the active balance has more to do with safety than the static balance.
That's right.
This is why, like when you're flying some sort of RC, that you need to monitor each cell individually, because when one cell reaches a critical voltage, you have to shut down. And that is technically a form of balancing, because you're not allowing one cell to go completely out of balance and destroy itself.
That is a great way into segment the other part of my question of cell balancing. Why is it important? If you didn't balance this pack with, now that you've monitored the cells and what you're putting them into the pack, if you don't have active balancing, what happens?
Well, so some battery packs get away without active balancing because they don't end destructively. So a lead acid battery, you can equalize charge and overcharge it to balance it, and it doesn't risk destroying someone's house. And so it's not as important. Now, in our newer chemistries, it's much more important from a safety aspect that balance is done properly.
Yeah.
Why a lot is put into it.
Even the safety aspect is obviously the biggest aspect, but from a electrical performance aspect, if you're whatever percentage out of balance you have in capacity is direct percentage loss that your pack is able to make use of. So, if we have a cell that's 5% lower capacity than the other cells in the string, or lower state of charge, then when we go to discharge, that cell reaches its minimum safe voltage 5% sooner than the rest, and so we have to stop the full string being discharged 5% sooner. And same thing if you're charging and one cell is 5% higher, then you would have to stop while the rest of the cells are only at 95% charged. So either balance direction up or down hurts you by the amount of the imbalance from an electrical storage perspective. The safety perspective is really the most critical thing, though. I actually we'll get into it, but I actually like when I see the BMS let a pack start to show imbalance that has a problem, rather than forcibly correcting that imbalance.
And that kind of brings in that, normally a balancing circuit is just there to make up for minor manufacturing defects in the cells. It should not try to hide problems. It should not make up for problems. If you have a cell that has self-discharge, a balancing circuit will hide it visibly from you unless you have something that monitors how much cell balancing is happening.
Yep.
But it's more, in proper end designs for battery packs, it's a danger to know that you have a self-discharging cell, and at that point the battery pack should be flagged for shutdown.
Yep.
That's a lot different than the hobby packs, where we just try to use our RC packs until they die. But they're also different scales of size.
Yep.
I wanted to go back to, you had mentioned some applications don't need cell balancing as much as others. How does anyone make that call on whether they need it or not?
In a perfect world, if you had all good cells, you'd never need your cell balancing circuit to do a thing for the whole life of the product. So in a perfect world, your amount of balancing you'd have is zero.
Yeah.
And you'd never need any of that circuitry. In practice, though, the self-discharge rate, while we try to make it zero in a cell, right, the actual electron mobility from anode to cathode in the cell tries to approach zero. There's impurities in the solvent, there's nucleation sites on cut foil edges and surface of active material. And these things all have imperfections where we lose some electrons. And so, this is the self-discharge effects. Now,
Or the gas evolution.
Yep. Yeah, splitting gases and electrolyte side reactions. All of these things cause self-discharge.
So I'll go into one of my own personal applications. I have a off-grid teeny home that runs on battery packs and solar, and they are actually second life cells. And what I had done with these cells was I actually measured impedance and capacity on them and matched them myself into groups. Since this is a very large battery pack and it's running for a very long time and it's my personal money, I refer to BMSs, or battery management systems, that fail to function as battery murdering systems. And the reason why is if you have circuits that are capable of discharging your cells, there's a chance they destroy them.
Yep.
And so currently on my teeny home, I check balance with a balancing board that I plug in physically and double check manually. And this way, I'm not trusting any sort of electronics on my battery pack. I still have things that shut down my battery pack due to LVC low voltage cutoff, or HVC, high voltage cutoff, but I have no active balancing circuits in fear of them not shutting off and destroying my expensive battery pack. And this is a very rare point of view, but this is my point of view from seeing very many balancing circuits fail to function properly and do more damage to the cells than they were intending to save.
That's a great example. And Bryan is obviously an expert and knows what to look for in the battery cells. It's what I'm hearing is basically when you are installing a cell balancing monitoring system, that it needs to have a lot of considerations that you're not going to kill it.
You're
kill
adding
the battery.
risk and failure modes.
Right.
And even if it's correct, let's say that the product was designed with no electrical or hardware faults, you could still have even the harnessing of that system have corrosion related faults, that cause fires or other risk.
But we're saying it's kind of a necessary evil because
in
you're not having a Bryan look at every single battery pack out there.
And that's it. I have to manually go and check my battery packs, which means that I have to. It's then my fault if it breaks, and I only have myself to blame. But then I only have myself to blame. It's a lot different
in production and mass
production systems. Yeah. So the other thing with my teeny home battery pack is because I have to sleep with it, they're also very safe chemistry cells. So there's a lot of other safety aspects on top of that. So I wouldn't suggest anyone just run out and run no cell balancing, because again, I do have LVC, HVC, and those are the bare minimum requirements for safety. But to get the most use out of your pack, as Luke was saying, if you want to actually charge and discharge it to full power and full capacity, then your cells are going to have to be in balance. So currently my teeny home pack, I start to lose some watt hours of capable capacity because I'm not balancing it actively, but that's okay as far as a trade-off to the peace of mind. Now, if I develop my own BMS and slap it on it, I might trust it. Maybe. Maybe.
Wow. So that kind of leads us into the next section you wanted to talk about. And maybe for the purposes of this, we're talking about in a production kind of environment with using the same kind of cells. How does one perform cell balancing?
The most cost-effective way,
Adger?
since we
hire someone.
Since we don't need, we've already talked about that, we don't need a lot of current. Even if you have many hundreds of amp hours of capacity in each of your parallel cell groups, you don't need a lot of current to balance this, because you're only balancing to keep up with a difference in healthy cells' self-discharge rates, which should be approaching zero. So, we've seen examples where 100 milliamps of balance current was overkill for a 120 amp hour capacity cell group, in that by overkill I mean that you could mask an issue that would have been better for the BMS to let that cell group die from self-discharge.
A frequently asked question we get is there a minimum or maximum value specified for cell balancing, or is this product specific?
It's mostly product specific, related to the internal self-discharge of the cell.
And the variance in it between cell groups.
The lithium-ion batteries tend to have a very low self-discharge, and so they're not as needed. But I do want to bring up one aspect that maybe a lot of our viewers have seen, and I want to explain it. And that's in RCs, you may find battery packs are really imbalanced a lot. And you may find that you need to balance them all the time. And the reason for this is those batteries are being abused very much so. So when you touch a pouch cell, you cause minor microscopic damage that starts self-discharge. So even by handling the cell, you've now created self-discharge that your balancing circuit is going to have to make up for when it's charging. And so in a lot of RC packs, you find that you always have to balance because your cells are dying. Those cells also don't last 1,000 cycles. This is where Luke and I are there's a line between like hobby cells and
EV
an actual
cells.
EV grade and class of cells. And the ones that we're talking about that don't require balancing are the EV grade class cells. They're not your hobby packs that you're flying on a drone.
And no matter how balanced or imbalanced your pack is, you still have to have your BMS make your decisions ultimately off, cell voltages, regardless of what your calculation may think the capacity is remaining in that cell group. HVC and LVC have to be king on all BMS decision matrix for safety reasons.
That was another frequently asked question we get is what metrics must the BMS make with operating decisions in respect to balancing?
It's, the best decision the BMS can make is when it finds there's some cell group it never turns the bleed resistor on for, and that there's, all the other cell groups it has to bleed frequently to keep them as low as that group that's never getting bled. That's the signature that you have a defective cell or a corrosion issue external to the cell. Either way, though, that's a sign that the battery should let that system, at some point it needs to flag it to stop charging and let it finish end of life. It has a problem.
And this is also why there are some battery packs that you may find in field where you open them up and there's only a dead cell or two, is the management system may have let it die for safety.
Yep.
Or the other flip of the coin is the management system may have murdered it. It's hard to tell at the end of it.
So is it possible to balance a pack too much, and what happens?
Definitely possible.
I'll give one scenario that's just inefficient. And if you were to balance at top and bottom and you were only using resistor-based balancing, then all that heat that you produce is just not energy that can be used in your system. And so there's extravagant active balancing systems that use little switching mode power supplies to try to save this efficiency. But as Luke came back to it, use good cells and you shouldn't have to balance. And
yep, your deviation in a healthy pack should be extremely tight.
What is the max imbalance rate for a EV grade pack that you usually consider for, let's say, an NMC cell?
Well, the cells that I'm used to working with, both in cylindrical and pouch type, they're received at voltages, tighter than 1 millivolt to each other. And after many years of use without any balancing at all, they usually are within a millivolt or two of each other. But that's an exceptional quality of cell in a packaged in systems that keep them at a uniform temperature without abnormal interconnect heating and other effects. Depending on the quality of design of the pack, you can see significant degradation differences between cell groups sometimes.
The only experience I have with that is a personal battery pack that I had ran for 6 years, cycling quite often, and it was an EV motorcycle, and the battery packs at the end of life appeared to have only balanced a couple amp hours across the entire 25 amp hour pack in the entire lifetime. And that's because the management system actually kept logs of every time a balancing circuit was active, and I could read that out. Most management systems don't have that kind of logging, and so it's kind of hard to tell at the end of life how effective the balancing circuit really was.
That's good feedback, and it leads into our next question, which is how do we design battery packs for efficient cell balancing?
Well, you start with good cells, that you keep them the same uniform temperature. You don't have asymmetric heating sources in their busing and interconnects, and that's your best approach to maintaining cell balance, because everything you do that's not that way to solve it, unfortunately, is a Band-Aid, because you're causing asymmetrical self-discharge damage in your cells, or you're accepting cell defects.
Right.
Either way.
Maybe for our viewers, the asymmetrical cell damage, like how would that occur in a pack?
If you have cooled places and hot places in the cell, there will be this asymmetry of use in your active materials, scaling to something like a factor of 2x for every 10 degrees Celsius of total imbalance. So even when it's just...
So you could start with like all the same matched cells and have them become unmatched.
That's right, because once, some area was located where it was heat islanded, and some face was located where it was cooled effectively, and now these cells that started matched have taken on different rates of aging, different rates of impedance climb.
Are there times not to balance the pack, like when you see these impedance variations or temperature variations?
So I don't like to balance below around 90%.
And then you also
charge.
Don't want to balance while in a active situation. If you have an active or dynamic imbalance, you don't want to react your balancing circuits on voltage drop due to load and impedance.
Yep, or voltage rise due to charging currents either. You've got to be under a no current situation when you measure balance and then engage your balance.
And then even then, like the battery pack should be at rest for quite a while.
Yeah, that's right.
Because all of your voltages will be changing, at maybe even hours, depending on the chemistry of the cell after an extreme overcurrent situation.
Is there a certain kind of circuitry or design that you prefer when performing cell balancing?
I like resistive bleed, where a small MOSFET is used to switch in and out a low, an appropriate value of ohm resistance to cause, some value well under 0.1% of the capacity of that cell string in current. So perhaps even 0.01% is more like a realistic current value for the amp hour capacity.
This is a bit of a billion-dollar question, and we've kind of covered it a bit here. Is mixing cells or using recycled cells to make refurbished batteries viable through many amp active shuttle balancing between cell groups?
I personally would never suggest it, but in the past I've tried, and it's just a lot easier to start with good cells. If you're going to put a lot of time in, or at least personally, if you're going to put a lot of time and effort into a battery pack just to have it die on you, it's really sad.
I gotta say, it's the kind of thing that an expert might do for himself if he had a free supply of something like that, but
at minimum you would have to start with high grade cells in their second life. Second lifing a low grade consumer cell might be riskier, but then the other two is with some of the new chemistries coming out for electric vehicles, they're quite dangerous to deal with by themselves. And so creating secondary packs without really understanding the exact chemistries and how they need to be treated could be risky.
Yep.
And just for clarity's sake, if I were to come to you and I said, I have an unlimited supply of the best cells in the world, and I have a BMS designer, but I have so many questions about cell balancing, how would you walk me through implementing that into a design?
You're going to have to sweep your self-discharge curves and find out what's representative on your cell stock. Every cell has some self-discharge, so once you quantify that bounds of what healthy cells look like, it's going to help you understand what a healthy BMS balance current would look like for your pack. That'll still allow you to flag, not so much balance current that it'll mask when you have a defect, because the BMS shouldn't be there to cover your defective cell issues.
And if you have an infinite supply of cells, that means you can match them very well into groups.
That's right.
I like this world where I have unlimited batteries.
Yeah, it would be nice, huh?
Yeah. All right, so we'll move into what the safety considerations are in cell balancing and battery pack design. We had kind of alluded to there's some situations where maybe you shouldn't do it. And let's say now I overdo it. What did I do wrong? What happens?
It comes down to gas production. If you have that defective cell, it's been discussed for multiple years now on trying to get an answer if there's a method that doesn't involve gas production when cells have self-discharge, but it appears to date we only know of types that do cause associated gas production. This means whether you're a cylindrical, whether you're a pouch, whether you're a prismatic, you have a finite volume to store gas evolution, and you'll increase in pressure until at some point you breach containment of electrolyte, at which point you
AKA explode.
Yeah. Yeah. In a nice situation, maybe you just spurt electrolyte into the assembly, but either way, this can cause a corrosion-induced fire hazard, which is unfortunately fairly easy to induce in the presence of electrolyte and electricity outside of a cell, especially with exposure to atmospheric humidity. For these reasons, it's best if the cell stays sealed in the pack, and this is the reason why we mentioned not overbalancing, is to keep the electrolyte, keep that corrosion fire hazard risk liquid inside the cell, rather than crutching it along with its self-discharge problem until the point that it's developed so much gas it's now breached this corrosive liquid into the pack assembly, generating a fire hazard.
And just to add on that, from the pack assembly too, is in large EV battery packs, it's easy to have 200 amp hours on a string. In that sense too, is if you have a balance wire and it's only going to carry 100 milliamps, you need to fuse at the battery, because if something happens with that balance tap wire and it shorts out, it has a 200 or plus amp hour battery pack pushing behind it, and that wire will evaporate if it's not fused. And it's not something you find on a lot of battery pack designs at the moment, but you want to fuse it, every wire coming out of the battery pack right there, and that includes your balance wires.
Yep, right.
And because the balance circuit is so small in current, it could be something very teeny, a thermal fuse, or even a fusible link of some sort, just something that needs to protect, because just because your balance circuit can only pull 100 milliamps
doesn't mean you can't pinch
if your
the
MOSFET
wires.
shorts or wires get pinched, it will flow more than that.
Yep.
And the higher voltage of the battery pack, the higher the risk you have of like a mid-pack string balance wire touching an end, and currents will get out of hand real quick.
Yep.
Do you have any opinions on battery safety sensor technology to detect cell venting, like recording dew points, humidity, pressure change, temp, and pack? So you had talked about corrosion and electrolyte squirting out. I don't know if that's the right word, but
it does.
Do those sensor technologies, like, do you think that could be a promising way?
I'll let Brian comment on that.
I personally have not looked too far into it. But the gases that are given off are kind of interesting. So hydrogen is one, and unfortunately lots of things give off hydrogen. So if you're trying to detect hydrogen, that's probably not the route. Other things like carbon monoxide is another gas that's produced internally as a byproduct, and that's another one that can just happen to be in the environment by itself.
From non-battery causes.
Acetylene gas, like blowtorches, is another gas that's formed within there, and that also breaks down very rapidly in the air and decomposes. So there's not too many
The
materials to
VOC
trace.
the VOC sensors pop for the electrolyte solvent base pretty readily, but they also pop for
Like
many
humans.
things
Right.
readily.
So a paint pen, like a shake-up paint pen, actually has a solvent that's almost exactly the same that's used in some lithium-ion batteries. And so if somebody used a paint pen around some of these sensors, it may trigger it. If you're in a grid-tied storage situation and you have a sealed container and it's a controlled environment, then maybe some of these gas detectors might be useful. I personally have not used any, just because the environments that I am trying to implement battery packs are not clean enough to try to take sampling of the air.
Yep.
That's good input. And I totally understand where those sensors, like what the niche of technology they want to fit in. And I'm excited to see that grow and learn more about it. Is it possible to predict thermal runaway or problems prior to this off-gassing, or like not even needing a sensor like prior?
If thermal runaway is somebody stabbing it with a knife, then no, you probably won't detect it.
I mean, from like a cell health perspective, like is there any red flags that would give away to be like this pack is on its way out?
The signature of having all the other balance resistors need to turn on except one group always, and that group always leads discharge. There'll always be some cell in a natural distribution of healthy cells. There'll be some cell that has a healthy but greater than the other healthy cells discharge. So this would be your noise risk of false flagging, and once you understand that noise distribution among healthy cells, you can understand what bounds definitely represents an unhealthy cell, and whether it's corrosion, whether it's internal defects, whether it's a separator problem, a foil edge problem, a coating problem, broken SEI problem, formation problem, whether the envelope got breached and humidity's intruding into it. All of these things will cause the observance of voltage suppression in that cell as it has increased self-discharge, and this, it is a signature that you can watch for to try to preventatively, stop your pack from, the BMS has to tell at some point, no longer are we going to charge this pack, and that's really the way, you have to safely end the life of that system. Let them continue to discharge it, but it won't charge again. This ends up leaving it in the safest condition again.
I like that you always say the best death for a battery is a graceful one.
That's right.
Just let it die in a way where it does not have thermal runaway.
Yep. No matter what fancy balance circuit you got, it won't fix your foil defect. It won't fix your water in the cell. It won't fix your corrosion, internal or external. It won't fix any of the problems. It won't fix your separator problem. All it can do is mask those real safety concerns from being able to be flagged and have that pack die gracefully.
The energy has to go somewhere.
Yep.
And if you're losing energy that you have to balance for, more than likely that energy is going to destroy the cell.
Yep. That energy is not going into some pathway that doesn't escalate, right? It's causing degradation that leads to more degradation. It is an accelerating spiral, and it will end in fire if you misuse it by just forcing balance to be numerically correct at your voltage taps while you have a serious problem happening.
Thank you. Is there anything else that you'd like to say about cell balancing, whether it's how you do it, when you do it, that maybe we didn't cover in our frequently asked questions?
Always refer to the operating manual from the cells from your supplier.
Yeah.
Step 1, read the instructions.
Yeah, they'll probably have good advice on what bounds they like to see voltage in.
And who knows, there might be a new chemistry around the corner that we may not know of that requires different forms of balancing. So make sure you just understand what you're working with.
Yep. Your cell manufacturer will help you understand what healthy self-discharge should look like too, so that they know very well if they see excessive self-discharge, it means they made a defect.
And if you can't find a data sheet for your cell, it may not be a high quality one.
Yeah.
Fair enough. It's a bit more an advanced concept. Let's say there's a dual chemistry cell out there that's kind of been a hot topic in the industry. What are some of the challenges of cell balancing either a new chemistry or a dual chemistry cell?
Oh man,
I honestly haven't looked into this yet.
It sounds awful.
Okay, that's fair. I just wanted to see if you had an opinion there.
I would
increasing complexity, increasing ways of failure.
I would need to sweep the cell many times at different temperatures and C rates, and understand the nature of that cell's relationship, because I haven't tested a single dual chemistry cell yet to date, and I think there's good reasons for that too, because most dual chemistry cells only actually get to operate on one of the two halves of their cathode material at a time. So it's kind of like, I would say the dual chemistry from a functional concept is maybe needs reconsideration.
Thanks for that. I appreciate your time today, and we hope that this podcast has been helpful to you, and we look forward to talking to you about your fun projects that you have out there in the world. Thank you for electrifying our world.
Thank you for the opportunity to share. Appreciate it.